All right, guys. Sorry I'm not here today. I feel bad about that, but I'm at a volleyball tournament, and I'm sure you're just fine to be without me. Um, oh gosh. Oh, geez, Louise. Well, there I am. So if that hasn't reminded you why you're glad I'm away today, then now you have it. But anyway, so I'm away today. We're going to finish yesterday's note. So you can pause this video for a second and make sure you have yesterday's note out and go with that. Okay, well, let's get rid of that. Whew, that's better. So, sorry. Oh, yeah. Okay. So yesterday we started talking about the idea of putting atoms together. And when we put atoms together, we call that the process of bonding. Right? Because we looked at that and we said that any atom that has a valence orbital that isn't full isn't stable. Right? We went to the machine in the back, the centrifuge, and we looked at sort of an unbalanced load and what that looks like. So to become stable, atoms have to form bonds with other atoms. And these bonds involve either filling or emptying that outer shell, that valence shell. And so we said one way that can happen is by the giving and taking of electrons. And we looked at an example of when lithium and fluorine come together. Lithium, if we draw a Lewis structure of it, looks like this. It has only one electron in its outer shell. And on the other hand, fluorine looks like this. It has 7. So one of them is electron poor, and the other is electron rich. And for that reason, the one that's electron poor is very close to having an empty shell, so it can just give away its one electron. And the one that is electron rich is very close to having a full shell. It can receive it. And when that happens, now they can both be stable. The lithium is stable because it has an empty shell, and the fluorine is stable because it now has a full shell. And in both cases, that's stable. But in both cases, because lithium lost an electron, and electrons are negative, it now has a positive charge. And because fluorine gained an electron, and electrons are negative, fluorine now has a negative charge. A reminder that when we draw these out, when we show what has happened, on the left, before they've given their electrons away, these are just atoms. On the right, we call them ions because they now have a charge. And whenever something has a charge, we draw square brackets around it in its Lewis structure, and we write the charge at the top. So in this case, the lithium has taken a positive charge, so we draw square brackets around it. We put the positive one there, and we call that the cation. The cation is the name we give to a charged particle that has a positive charge. The fluorine, with its extra electron here, now has a -1 charge. So we draw square brackets around it and write the -1. And we call it now the anion because that's the name that we give to a negatively charged particle. So that's the basic idea with forming an ionic bond. And we looked at another example, which was magnesium and chlorine coming together. And the same idea, magnesium has 2 electrons to give away. In this case, chlorine has 7 electrons. It only wants to gain 1 more. And because it only wants to gain 1 more, when magnesium has given its first electron away, which gives us a negatively charged chlorine, it still has an electron left that it needs to get rid of. And for that to happen, we need to get a second chlorine. And for that reason here, we see that the formula of this is MgCl2, because it took us 2 chlorine atoms to get rid of those electrons, because each chlorine could only take 1. But all the same, we still call the positively charged magnesium a cation. In this case, it takes a charge of +2, because it didn't get rid of 1 electron, it got rid of 2 of them. And we would call both of the chlorine ions an anion because they have a negative charge, because each of them has gained another electron. And then finally, you did an example yourself, aluminum and oxygen. Very good. So before we move on, I want you to try another, but I should mention that what holds this together what the ionic bond itself is the natural force of attraction between opposite charges. If you have a positive thing near a negative thing, there is a force of attraction between them. They will actually move together. And the reason that happens is just one of the fundamental forces of nature. It's just true that anything with a positive charge attracts anything with a negative charge. So that's what holds this together. And that's a very strong charge. Like we said, ionic bonds are these rocks, right? They will just continue to grow like this. They'll continue to form these big crystal structures. And according to the recipe, right? In the case of lithium and fluorine, we said that for every 1 lithium, we get 1 fluorine. In the case of aluminum and oxygen, the recipe is a little different. For every 2 aluminums, there's 3 oxygens. But even still, that crystal structure could continue to grow, right? Just kind of like that, and you could just keep drawing it out. I want to give you one more to work on just as practice, and you can do this on a piece of lined paper. You can do it on a whiteboard if you have it, or up on the whiteboards in the room if you'd like. That's fine. But I'd like you to try and show me what happens when calcium bonds with nitrogen. So pause the video, take a minute, and see if you can draw this out. Work together, be a team, and show me what happens when calcium bonds with nitrogen. Oh, sorry about that. Okay, so pause the video, then we'll come back momentarily, and we can take a look at it. All right, so we're back. What was only a few seconds for me, hopefully has been a little bit of time for you. And what we could do to answer this is we could look at the periodic table. Because we've been asked to look at calcium bonding with nitrogen. So let's give ourselves a periodic table here, and let's look at each of these. Calcium has a chemical symbol Ca, right? And if we look at its location on the periodic table, it has 4 shells, but in that 4th shell, it is the element that has 2 electrons in its outer shell. So we would get Ca, and it should have 2 electrons. And on the other hand, we could take nitrogen right here, and nitrogen has 1, that's really hard to see, 1, 2, 3, 4, 5 electrons in its outer shell. So nitrogen should look like this. N, and then 1, 2, 3, 4, and a 5th. And if we look here, this is another case that doesn't work all that nicely because calcium only has 2 electrons to give. So these become a bit of a puzzle where calcium will give its first electron to nitrogen, and then it will give its second electron to nitrogen. And when it does that, the calcium now has no more electrons to give, and I'm not happy with where I drew those arrows, so I'm going to try that again. Let's say the first one goes up here, and the second one goes there. So now we would have a second electron here, and a second one there. That takes care of both of calcium's electrons. So calcium will now be stable, because we said anything with an empty shell will be stable. But to do so, it had to give away 2 electrons, and when you give away negative things, you become... Yeah, that is entirely correct. You become positive. In this case, it takes on a charge of +2. But the nitrogen still needs 1 more electron to have a full shell. It now has 1, 2, 3, 4, 5, 6, 7. So the only thing we can do is have another calcium. And that calcium will also have 2 electrons. And it will give 1 of them to nitrogen, at which point nitrogen will now have a full shell. So that nitrogen is stable now too. We can draw it here, nitrogen, and it will have its original 5 electrons, 1, 2, 3, 4, and the 5th. And then it will have the 2 electrons it got from the first calcium, and it will have the 1 electron it got from the second calcium, and it's now stable. Because it gained 1, 2, 3 electrons, it's taking a negative charge because electrons are negative. and -3 charge because it got 3 of them. The problem is this calcium still has an electron left, so it will bump into another nitrogen. Now that nitrogen, like the first one, is going to have 1, 2, 3, 4, 5 electrons. It will take the first of those. It will take one more electron from this calcium. Now that doesn't make the nitrogen stable. The nitrogen only has 2, 4, 5, 6 electrons now, so it's still not full. But that does have the effect that this calcium is now stable, right? It's lost both of its electrons. So that calcium can come over here, and it will take a +2 charge because it gave away 2 electrons. And now, since we need more electrons, what we're going to need is another calcium. And here it is. It's got 2 electrons, and it's going to donate both of them to the nitrogen. There's one, there's another, and now the nitrogen has a full shell. So its original 1, 2, 3, 4, 5, and then the single electron it got from that first calcium, and then the 2 electrons it got from the next calcium. And because it had to gain 3 electrons, it will take a -3 charge, and this calcium now will be there, and it will have a +2 charge. So altogether, it takes 3 calciums for 2 nitrogens. And the way we write that as a formula is we say Ca3N2. That's the formula of the ionic compound we get when calcium and nitrogen bond. So that's still a little tricky, and do not worry if that's stressing you out. This is not something we're going to teach once and then be done with. We're going to get a lot of practice. In the coming days, you'll get a lot of practice with this, I promise. So, that is ionic bonding. Ionic bonding is what happens when atoms share give and take electrons so that they can either fill up their valence shells or empty their valence shells. But there's actually another way to fill up the valence shell, and that is not by giving and taking, but by sharing. So, for example, if we have nitrogen and fluorine, so we're just going to make a little note here and say electron-rich atoms, which are the ones on the right side on the periodic table, don't give away electrons. But they will share electrons with each other. And so we can look at this example. Nitrogen and fluorine. So if nitrogen is here, we can look at the periodic table. And like we already saw, nitrogen has 5 electrons. So it's got 1, 2, 3, 4. I'm going to put a 5th up here. And we said we want to react this with fluorine. Well, we'll put a fluorine right here. And fluorine has 1, 2, 3, 4, 5, 6, 7. 7 electrons. That's what we see here, right? Nitrogen had 5. Oh, gosh. Oxygen has 6 electrons. Fluorine has 7. So we can draw those two Lewis structures just like that. And what we'll see is that nitrogen won't give an electron away, and neither will fluorine give an electron away. They can't do that. So what they do instead is they will share electrons. Now, from fluorine's perspective, it has 1, 2, 3, 4, 5, 6, 7, 8 electrons, because this green electron is now going to orbit both of them in a figure 8, and this purple electron is going to orbit them both in a figure 8. That's a bit of an oversimplification, but it works, which means that from fluorine's perspective, it has all the electrons it needs. Now, nitrogen doesn't, but that's okay, because we can always just get another fluorine. And this fluorine here, I'm going to draw its electrons in gold just to differentiate them, has 1, 2, 3, 4, 5, 6, 7. So again, to get its full shell, it can simply share this pair. Right? So again, these are shared between the two atoms. Now, from this fluorine's perspective, it has 1, 2, 3, 4, 5, 6, 7, 8 electrons, and so it has a full shell. Nitrogen still doesn't. From nitrogen's perspective, it has 1, 2, 3, 4, 5, 6, 7. It still needs one more. But that's okay, because again, if we're reacting with fluorine, we can just get another fluorine. And I will draw these ones in, well, I don't know. Let's say blue. And it has 1, 2, 3, 4, 5, 6, 7 electrons. And again, it can simply share this pair. And now, everything involved has the full complement of 8 electrons. So now, all of the atoms have a full shell of 8 electrons due to sharing. Okay, now, the shared electrons orbit both atoms which holds them together. This is a much weaker bond than an ionic bond. Now, the thing I want to note for today is that this sharing here, which I'm introducing today, I don't expect you to be able to figure this out on your own just yet. And this is important, so I'm going to turn my camera back on, which is horrifying to me too, so I apologize in advance. But I want to stretch this. This new concept is a tricky one. It's complicated, and we're going to spend a bunch of days on it. So when you go to work on the second piece, which is covalent bonding, understand that it takes a bit of practice, and it's much trickier than the ionic bonding. With the ionic bonding, it's a little bit of a puzzle, but it's a puzzle that only has one answer. And the thing we're going to show you in the next bit is that when you share like this, and you need to share your way to a full shell, there's actually a few different ways you can answer it, and that makes this tricky. So for the time being, the second half of this lesson, I don't want you to get super stressed about. All this stuff is going to take some practice. In fact, that's true for the first half of this lesson too. We've introduced this to you now, and then what we're going to do for a bunch of days after this is practice and learn a bit more. So please, 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 if this feels like it's overwhelming or stressing you out, don't get stressed out. You're going to do just great. All right. There we are. So one note is that the covalent bond is complex. It's complicated. And just to show you one example, if we put carbon together with hydrogen, they can get together in an infinite number of ways. There's just no end to how you can do this. And we're going to look at just two examples. The first one is the formula CH4. In other words, 1 carbon and 4 hydrogens. And if we look at how this works, carbon, if we go look at the periodic table, has not 1 electron in its outer shell, not 2, not 3, but 4 electrons in its outer shell. So carbon is going to look like this. 1, 2, 3, and then 4. And on the other hand, hydrogen, if we look at it, has only 1 electron in its outer shell. So, it looks like this. This is hydrogen, and it just has 1 electron. So now, hydrogen is actually pretty strong. It doesn't want to give its electrons away, so it doesn't. So what these will do is they will share these electrons. That's what we call that covalent bond. And covalent just means that co, together, and valent is the outer bond, the electron, or the outer shell rather, the electrons on the outside, the ones that we draw in the Lewis structure. So it means that it shares those electrons in the outer shell with each other. Covalent. So this is shared. And from hydrogen's perspective, remember that for hydrogen, 2 electrons is a full shell. So that's a happy hydrogen. Now we said we have how many of them? 4. So the second hydrogen could come down here, and it also has 1 electron. And these can share this pair. And now, this hydrogen, from its perspective, has 1, 2 electrons, which makes it a full shell. The carbon isn't full yet because it has 1, 2, 3, 4, 5, 6, and it needs to get to 8. But that's okay because we have 2 hydrogens left. In this particular formula, we have another hydrogen here, and it will have 1 electron. And of course, they can share this pair as well. And then finally, we have our 4th hydrogen, which can come up here. It has its own electron, and it can share that pair there. And the result is that we get this structure, where the carbon is able to share with each of the hydrogens, and it makes the formula CH4. This is a compound called methane. You don't need to know that, but it's in natural gas. So that's one way that we can put carbon and hydrogen together in a covalent compound like this, right? And as long as carbon has 8 electrons when it's done, it's happy. And if we look, it has, oh, sorry about that. It has 1, 2, 3, 4, 5, 6, 7, 8 electrons when it's all said and done. So it is now balanced. It now has a full shell. Without giving or taking any electrons, it just shared them. But, and I want you to see if you can figure out how to build this one, how to put it together, we could also build a totally different compound with carbon and hydrogen, which is C2H6. So take a minute, pause this video, see if you can figure out how we would put together C2H6. And if you think you've got it, after a few minutes, unpause this and I'll help you through it. And if you get really frustrated and you can't figure it out, then unpause the video and I'll show you it. Because again, it's okay if you're still struggling with this. All right, well, hopefully you've given this a try. Hopefully you got it. But if you didn't, that's okay. So we could come back to this idea here that carbon has 1, 2, 3, 4 electrons. And we could actually put the other carbon next to it here, which also has 1, 2, 3, 4 electrons. And they could share a pair of electrons here. And then there's 6 hydrogens, and they could go in all of these other places, because as we saw in the other one, every hydrogen has 1 electron. And so in each case, they can come up next to these, and in each of these cases, we're going to be able to share an electron between the hydrogen and the carbon. They'll share there, they'll share there, they'll share there, and here, and there, and there. A shared pair of electrons. And you'll often see this drawn, because this gets messy, where they will sometimes draw it just using a line to show a shared pair of electrons, like we see here. In fact, if you look up the formula of a chemical online, if you look for a Lewis structure of a covalent compound online, you'll see structures that look like this. So lines in Lewis structures are covalent bonds. In other words, it's those shared pairs of electrons. So we could redraw this structure over here like that if we wanted to. So that, again, is tricky stuff. The goal today was really to get this in our notes. And the goal was at least to kind of sort of familiarize ourselves with it. But the goal for today is not that you be excellent at this, all right? Learning chemistry takes some time. It takes some practice. So don't be discouraged if you're struggling with this a bit or confused by this. But do keep trying it. Oh gosh, what did I do? But do keep trying with it. So there's some homework attached, which looks for you to do some practice, all right? Drawing these Lewis diagrams like we did yesterday and today. The first half of that practice is all about ionic compounds, all about what we did yesterday, giving and taking electrons. And then the bottom is some practice with what we did today. Again, nobody's expecting you guys to be perfect at this. I just want you to do your best, all right? I'm around. So if you want to pop by the gym, if you have a question about any of this, you can feel free to do that. I am coaching, but there'll be gaps in the day. And failing that, I'll see you tomorrow. Have a wonderful day. Ciao.